A good day from SAIE Council Chambers, Johannesburg, and welcome to the joint meeting of the Institute of Electrical Engineers and the South African Institute of Chemical Engineers. A brief webinar considerations for attendees. First, go to your webinar control panel. The control panel will be located on the right-hand side of your screen, and you can post your questions via the Questions tab. At the end of the webinar, we would have a panel discussion and your questions will then be responded to. A recording of the webinar will be posted on the SAIE YouTube channel, the SAIE TV. And the third consideration for the day is that all attendees will receive a CPD certificate of attendance. So thank you, colleagues, and welcome to the proceedings for the day. My name is Pat Naidoo, and I'm going to share with you. And I'm your moderator for today. And I'm going to take you through the proceedings. And first, we'd have the protocol, and I would welcome Professor Lizelle van Wyk to come and say hello to us. Professor Lizelle, over to you, Prof.
Good morning, everyone, and welcome to this talk and panel presentation. I'm Lizelle van Wyk. I'm the president of the South African Institute of Chemical Engineers. SAIChE, as we are known as, is the voluntary professional organization for chemical engineers. And one of our missions is the advancement of chemical engineering as a discipline and also as a profession. And as such, the Hyrdrogen interest group has been established. I would like to take this opportunity to thank my colleagues heading up this SAIChE Hyrdrogen interest group in the South African Institute of Electrical Engineering that's making this event possible. And I would like to say enjoy this event and also encourage your colleagues to join our voluntary organizations and become active members. Thanks.
Thank you, Prof. Next, I have Mr. Pascal Motaselli, the Deputy President of the South African Institute of Electrical Engineers. Over to you, Pascal.
Thank you, Pat, Dr. Naidoo. Welcome, attendees. As the South African Institute of Electrical Engineers, we are delighted to co-host this online webinar event with the South African Institution of Chemical Engineers. Today, we gather here to delve into the exciting topic of green hydrogen energy. The aim of this webinar is to explore the immense potential of green power fuels, particularly in the context of Africa, and the opportunities that lie ahead. So today's webinar on green hydrogen energy exemplifies the power of virtual events as we bring together professionals, researchers, enthusiasts from various fields and locations to share knowledge and ignite meaningful conversations. We hope that this session will not only inspire, but also provide actionable insights that can drive innovation and progress in the realm of sustainable energy. We extend our warmest welcome to all the delegates attending this webinar today. We encourage active participation, questions, and discussions throughout the session. Together, let's explore the potential of green hydrogen energy and pave the way for a greener and more sustainable future. Thank you for joining us, and we hope that you find this webinar enlightening and engaging. Thank you.
Thank you, Deputy President. Thank you. Next, colleagues, we will bring on board the team that put together the assignment, Professor Maggie Chetty. Over to you, Prof.
Thank you, Prof. Naidoo. Welcome, everybody, to this webinar that is co-hosted by SAIChE and SAIEE. I'm Professor Maggie Chetty. I am a council member of SAIChE, and I'm also heading the Hydrogen Interest Group that was part of our strategic plan as a VA for SAIChE, which is for chemical engineers in South Africa. So the aim of putting together the interest group was to serve, of course, the members of SAIChE, and that was to provide a platform for the members to grow and to improve their knowledge with regards to hydrogen. But beyond that, we had individual goals. But I think as engineers and as professionals, you cannot work in isolation. So this collaboration with the Institute of Electrical Engineers is also to help bring the technologies together, bring people together. And this is a start of a series of webinars, which we hope that can start conversations so that we can paint the roadmap for South Africa in terms of hydrogen and also Africa. Thank you.
Thank you, Prof. Thank you. Let me pass to David Wright, who will introduce our guest speaker. Over to you, Dave Wright.
Great. Thank you, Pat. Good morning, ladies and gentlemen. It's my pleasure and privilege to introduce Dr. Burce Young, our speaker this morning. Burce is a PhD Chem-Eng from Wits, and after having 5 years as an academic at Wits, he moved to SAIChE, where he spent 30 years working in a variety of fields, including development and commercialization involving pioneering process technologies. Since April 22, he has joined the African Energy Leadership Center at Wits Business School, where he's exploring the technical, economic, and business risks associated with the novel and competing technology options for the energy transition in order to understand which will prevail and which won't. So Burce is ideally placed to give us insight into the role that green hydrogen is going to play in the decarbonisation process. And we really look forward to hearing from you, Burce. Thank you.
Thank you, Dave. Thank you. Colleagues, it's my honor to hand over the panel to Dr. Burce Young. Burce, I'm making you the presenter. Thank you.
Okay, can you see my screen?
Yes, we can see Burce, not your screen as yet. Yes, we can see your screen.
So thank you very much. I'm quite humbled by the large attendance list here, and I'm very grateful for the opportunity to speak to you today. And so I would like to start by saying that done quite a lot of work on green hydrogen. Actually, through the years when I was at SAIChE, there was a previous wave of interest in green hydrogen in the early 2000s, and I was involved in it then. And so my interest in green hydrogen is almost 2 decades old. And then I've dipped into it over time, over the last 2 decades, because SAIChE always had an interest in green hydrogen. It was always a topic of conversation. Then I'd just like to introduce this presentation that I'm giving today. It has evolved from a presentation that I gave at the SAIEE conference in November last year. But since then, I've done a bit more work on it and given it a fresh coat of paint and added to it a bit. And this is actually also a lecture that I gave very recently in a decarbonisation course to our postgraduate students. This is the absolute latest version of this presentation. And so and then I would also just like to say that my colleague, Professor Diane Hildebrand, has also kind of been my sounding board on this and helped me check my calculations and my thoughts. And so she's been extremely helpful to me in pulling all of this together. Okay. Let me check that I can move on. Let me just put this into presentation mode. Okay, I hope that you can see everything and that we're in presentation mode. All right. So let me start with an executive summary So I'm going to tell you what I'm going to tell you, and then hopefully when we go through the presentation in more detail, I will justify all of these statements. But I think it's useful to start with this executive summary to contextualize this whole thing. Okay, so first of all, green hydrogen is enjoying a resurgence of interest as a potential central pillar in the renewable energy transition. And I think that the large attendance today is testament to that. So it's definitely of huge interest as we go into the just energy transition, as we talk about decarbonisation. You know, green hydrogen has a potential role to play, and there's a lot of interest in it. Then I'm going to talk about the fact that the production of green hydrogen at the multi-gigawatt scale, and I think it's very important to emphasize the multi-gigawatt scale required, is technologically challenging and capital intensive. And I hope I'll be able to unpack that and show some of the latest thinking on it. And then very importantly, I'm going to talk about the cost of green hydrogen, because that's absolutely essential to the discussion. And so the current levelized delivered, and it's important that we consider delivered, okay, not at the factory gate, but delivered. Cost for green hydrogen is plus or minus $8 a kilogram, which is roughly equivalent to an oil price of $400 a barrel. And I think that is such an important fact that we need to emphasize, and I'll emphasize it many times, that green hydrogen delivered as things stand today is not cheap. Okay, and then the forecasts for dramatic decreases in both the costs of producing and transporting hydrogen are uncertain. And I hope to be able to unpack that, and that's an important theme that's going to come through this talk. Throughout my, my 30-year career, I've got a few things to say and for us to think about when it comes to forecasts, okay? Because forecasts are always uncertain. And then very importantly, we're going to delve into a bit of the issues of what the competing options to green hydrogen are, and specifically some discussion on the issue of direct use of green electricity being the most prominent, okay? So, for the green hydrogen evangelists, they talk about, that green hydrogen can be used for so many applications, and that is true. But you also need to consider the alternatives. And in going through this presentation, I will have some examples where we can look at how green hydrogen stacks up to the direct use of electricity for certain applications. And then I'm going to make the statement that the use of green hydrogen is a complete solution, and I mean as a complete solution for all the applications which we'll unpack in this presentation in the renewable energy transition, is potentially overhyped. Then I'm going to talk about something which I've through my 30 years at SAIChE have got the T-shirt when it comes to pioneering mega projects. Okay, there are very significant mega project business and execution risks for pioneers in multi-gigawatt green hydrogen. And then, lest I be accused, fairly or unfairly for that matter, of not being sufficiently enthusiastic about green hydrogen, I want to emphasize on a positive note. There is a role for green hydrogen in hard to decarbonize areas such as nitrogenous fertilizer, and there's some other applications as well. So it's not as if I'm trying to say that there is no role for green hydrogen. There is a role for green hydrogen in certain applications, but we will talk about how do we prioritize and what should we be doing first. Okay, then just a quick a contents page, which I'm not going to spend a lot of time on, We're going to talk about the industry hype and the forecasts. We're going to talk about why hydrogen is a good fuel. Then just a little bit about the hydrogen rainbow and green hydrogen, how it fits in. And then I'm going to talk about why the oil and gas industry likes hydrogen, okay? Because they're definitely punting it. And I mean, in this political world that we live in, things are always political, and there are various groups lobbying for certain things. There's a lot of money being put on the table by governments and subsidies, and so it's a very competitive space. Then we're going to talk a little bit about green hydrogen production, and then we'll talk about what does green hydrogen cost, and can its cost be reduced? How do you transport it, and what does it cost? What should green hydrogen be used for, and all the applications, and Michael Liebrich's ladder. And then I'm going to talk about the iron law of mega projects and how they will apply to green hydrogen projects. And then I've got some other factors to consider and backup slides. So let's first of all talk about industry hype and ambitious forecasts. They have a checkered history in the energy industry, and so you need to dig deeper. So I just start off with a bit of a cartoon. In terms of the hype, hydrogen is the answer to all our problems. And so just an amusing cartoon to start the discussion. So there is a developing consensus from COP26 and the oil and gas industry that green and hydrogen will play a pivotal role in the just energy transition. So I provided some references there, but there are hundreds of references, about the coming green hydrogen economy, and that it'll play an enormous role in the just energy transition. But then I just want to step back and say, okay, but consensus can be overrated, and there are many examples, but I'll pick this one. The fast breeder reactor, the nuclear reactor, is an example of a prolonged and costly innovation failure. In 1974, General Electric predicted that by 2000, about 90% of the United States electricity would come from fast breeder reactors. And it was not only General Electric, it was the general industry and consensus, government consensus, that nuclear energy would take over the world. And there were even statements made like that nuclear energy would be too cheap to meter, and so we would kind of have free electricity. Imagine that. And there I reference one of my favorite and interesting authors, Václav Smil. I've read most of his books. He's quite a controversial figure, but certainly, if you go and look at his book, Numbers Don't Lie, it is an interesting book, and he's not an author to be ignored. And then I will say that the current global wave of interest in green hydrogen is the third wave, with earlier waves having occurred in the 1970s and early 2000s. And I was part of the wave in the early 2000s at SAIChE. Okay, and then of course, not everyone agrees that hydrogen is the answer, and it has even been accused of greenwashing and that it is a cult. In previous versions of when I presented some of this material, some people actually became quite offended when I said, "Oh, so are you calling green hydrogen a cult?" And then they got emotional and offended. So my intent is not to offend, I can assure you, and I'm not necessarily saying hydrogen is a cult either. I'm just trying to point out that there are quite some strong views out there. Okay, but those people who are calling hydrogen a cult are often strongly argue that by and large the energy future is likely to be electrical rather than hydrogen, except for some niche hard to decarbonize areas. So it's just, I think it's worthwhile being aware of both sides of the debate, and that there's quite a vociferous contingent out there saying that hydrogen is a cult. And then to talk about the fact that the EU has recently announced it intends to produce 10 million tons per annum of green hydrogen within the EU and import a further 10 million tons by 2030. So, you know, there's government involvement. It's not only the EU, Japan, and the United States, but we're going to talk a bit about the EU because I think it's quite relevant to South Africa. And then the South African and German governments, together with SAIChE, have launched a collaboration to make sustainable aviation fuel, which is based on green hydrogen, and that's interesting. Okay, but the point I want to make here is in the kicker box on the bottom right. There are competing views here, and there are going to be winners and losers, and who is right, and the answer matters. And so I'm hopefully going to be able to provide some views to help you navigate this emerging debate about what the future of green hydrogen is. So let's just start with why is hydrogen a potentially good fuel, okay? And energy density, whenever you talk about a fuel, is front and center. So, and one also needs to look at energy density, both gravimetrically, mass energy density, and volume energy density, and both matter, okay? I presume I scarcely need to go through the definition of energy density, but for completeness, let me do that. It's, of course, the amount of energy that can be stored in a given system, and it's measured in energy per volume or per mass. And so here I've just listed, it's not a comprehensive list, I've just listed some relevant fuels, and I've listed them in decreasing volume energy density. And then just because I can and I'm irreverent by nature, I started with antimatter, okay? And so if only we could access antimatter as a fuel, I think all our problems would be solved, because its energy density is off the charts. Of course, it's totally impractical. So let me get back into the real world and look at things like diesel and petrol and LNG, and you can see why diesel and petrol have evolved as such attractive fuels, because they have good energy densities, both in terms of mass and volume energy density. There you can see we go down to LNG, and that's worse. Liquid ammonia, that's potentially being touted as a fuel as well, quite a lot less. And there you can see hydrogen liquid at -253 degrees C. It has a very nice mass energy density, and sometimes, you know, in misleading articles in the press, they tout that, and of course it's true. But then when one looks at the volume energy density, then it's not that great. Okay, so it's quite a lot worse than your energy, than your diesel and your petrol. And then I've just put one of the best batteries out there, which is fairly experimental. You can look at a zinc air battery. You can look at hydrogen at 700 bar, because, you know, hydrogen at -253 degrees C is pretty challenging. Then we can look at where lithium-ion batteries are, and then I also just put water at 100 meters dam height, because of course pumped hydro is a very important way of storing energy as well. So just a final statement on this, you know, hydrogen has a good mass energy density, but a relatively poor volume energy density, and requires extreme storage conditions, which makes it expensive to store. Of course, hydrogen's main attraction is that it burns cleanly, producing only water and no greenhouse gases. And that's, of course, why we're interested in hydrogen. So now let's talk a little bit about this, you know, this hydrogen rainbow. And as I presume all of you know and are informed, that when we talk about green hydrogen, we talk about starting with renewable electricity, be it coming from wind or solar, and then we separate the water into hydrogen and oxygen by electrolysis, and that's called green hydrogen. Okay. If we start with natural gas, and I've put there steam methane reforming, it's not all steam methane reforming, but that is the state-of-the-art technology, and most of the hydrogen produced today comes from steam methane reforming. And you can see the numbers that I've put in there are the amount of production today of green hydrogen. So less than 1% of the world's production of green hydrogen, of hydrogen, is green hydrogen, and about 71% of it comes from natural gas. If you make it from natural gas, you release a lot of CO2 into the atmosphere, and that's called grey hydrogen. And then some of the world's hydrogen, and for example in Sasol's case, comes from coal gasification, and 27% of the world's, about 27% of the world's hydrogen comes from coal gasification, which releases even more CO2 into the atmosphere, and that's called black hydrogen. Then if you capture the carbon from either grey or black hydrogen, or from natural gas production or coal production, and you do carbon capture and storage, then that's called blue hydrogen. And less than 1% of the world's current hydrogen production is blue. So then let's go into to be comprehensive. When we talk about the hydrogen rainbow, there literally is a rainbow with a whole host of colors of hydrogen, and you can see there that we are, just for completeness sake, we have things called purple, pink, and red hydrogen, and I'm not going to go into their definitions in great detail, but they use nuclear energy and are somewhat speculative. Some of them are somewhat speculative, and white hydrogen refers to naturally occurring hydrogen, just to be complete. Okay, but I think the message is that, you know, almost all hydrogen produced today is grey or black and is produced from fossil fuels. Green hydrogen production is very, very small. Okay, so now I'm going to talk a little bit about why the oil and gas industry likes hydrogen, and we're going to talk about the hydrogen that's made today. Okay, and the current hydrogen production today is about 90 million tons, and as I mentioned before, most of it comes from natural gas, some of it comes from coal, and a little bit comes from oil. Electrolysis is a very, very small part of today's production. Okay, and then let's look at, look on the left-hand side of that Sankey diagram. You can see what the feedstocks are. Let's look at the right-hand side of the Sankey diagram, and have a look at what it's used for. Okay, and there you can see its main use is in refining. Okay, in hydroprocessing, hydrocracking, and hydrogenation. Okay, so it's used in refining to make fuels, and specifically also as we make cleaner fuels, to remove sulfur from diesel and from petrol, for example. You need to use hydroprocessing or hydrogenation processes. So that's the main use of hydrogen, and it's then usually produced in situ at the refinery. Sometimes, for example, the US Gulf Coast, hydrogen is produced as a utility and supplied as a utility to refineries in the Gulf Coast. But in most refineries, it's produced in situ. And then, of course, the other big use of hydrogen is ammonia. Okay, and we'll talk more about ammonia. But ammonia, of course, a fertilizer and explosives, but by far mainly fertilizer is the main application of ammonia. And so those are the two biggest applications. I will then mention, of course, it's used to make methanol. And so, you know, the entire methanol industry is based on hydrogen production. And then you can see there's some other direct reduction of iron. That's a developing field and a very interesting use of hydrogen. And there you can see there's some other uses. So that just gives you a picture of today's hydrogen value chain. The data is from 2019, and maybe it's changed a little bit by 2023, but I think that this picture is still largely true. So let me then go maybe into a slightly more political realm and address the issue of why does the oil and gas industry like hydrogen? And why are they lobbying so hard for it? Well, the first obvious statement is almost all of today's hydrogen is produced from fossil fuels emitting CO2. So the current oil and gas industry, they're the incumbents. They've been making hydrogen for decades, okay? And it's part of their business. The use of the hydrogen as a fuel fits with the oil majors' current business model. They control the fuel production, supply, and the wholesale and retail distribution of hydrogen fuel. So it just fits with the way they do business. The oil majors can supply grey or blue hydrogen to transition to green hydrogen. So the oil and gas industry paints a story of continuity. We make hydrogen, and initially we can say supply you with grey, then blue, and ultimately we can transition to green hydrogen. So there's an attractive continuity to that, and there's a logic to what they say. But then I come to my fourth bullet point, the direct use of electricity for battery electric vehicles and trucks represents an existential risk for the oil majors. Their wholesale and retail business could break down completely. Now, why do I say this? You can of course convert all the service stations that the oil and gas industry has to battery charging for electric vehicles, and to an extent it's already happening, and you will find charging stations at some service stations, particularly overseas, but even in South Africa, that is starting to be rolled out a little bit. But the problem is that that's not the only place you can charge your vehicle. You can charge your vehicle at home, although not fast charging, but you can charge your vehicle at many other places. You can charge it at your office building where you're working. You can charge it at a shopping center. And a value proposition of shopping malls will surely be, well, why don't you come and do your grocery shopping or your shopping? And while you're doing that, just plug in your electric vehicle and charge your vehicle while you're doing your shopping. So I think with a little bit of thought, it's obvious that the service station model is not the complete answer to battery electric vehicle charging, and so their whole business model is at risk. So I think it's fair to say that the oil and gas industry has a strong vested interest in promoting green hydrogen to try and ensure their survival. And then I will just mention from the previous slide, that and that's what I mean by the referenced IEA report from which I took that Sankey diagram, did not capture the fact that Sasol Secunda is a major producer of black hydrogen, so which could be used for process development and market seeding for later green hydrogen. So from a Sasol perspective, you know, Sasol can certainly supply a lot of hydrogen, albeit not necessarily green initially. Okay, of course later they could transition to green hydrogen. So I just make the perhaps controversial statement in the kicker box at the bottom that the oil and gas industry has a vested interest in promoting green hydrogen. So let's talk a little bit about green hydrogen production. And I've just got a very simple infographic there saying that you start with renewable electricity, and you produce direct current. The only feeds are renewable electricity and water, and then you put that through an electrolyzer, which is about 70 to 80% energy efficient, and then you make hydrogen and oxygen, and you separate the hydrogen and oxygen, and you've got green hydrogen. So it's quite a simple process in principle. And then I will just start talking about the fact that, of course, today the largest commercially available electrolyzer stack is about 2 to 5 megawatts, with plans for 20 megawatts. And I haven't kept totally up to date whether they might even be going more than 20 megawatts, but certainly the intent is to scale this up. So electrolyzer technology is not mature, and there are different technology options under development with no clear winner at this stage, and I'll try and justify the statement in the next slide. And the efficiency, durability, and cost for gigawatt scale electrolyzers are a significant challenge. And I will also try and justify that statement in my next slide. And the point that I'm going to make, and I'm going to state it here, and then I'll try and justify it in the upcoming slides. Pioneers of gigawatt scale projects face significant technology risks. So let's look at the various types of technology, and I've shown 4 technology options here on the left-hand side of this slide. But before I talk a little bit more about that, I want to look at the statement that's made in the top right kicker box, and I've put inverted commas around it because it's not my statement. This statement comes straight from IRENA, okay, the International Renewable Energy Agency, who are, you know, evangelists for renewable technology. Although I have to say they have produced extremely comprehensive and good reports, in my opinion. So they say each technology has its own challenges, from critical materials to performance, durability, and maturity. There is no clear winner across all applications. So here we have IRENA saying that this technology is not mature, and there's still there's no clear winner, and the technology is not mature. So then let's just look at the 4 technologies that that they looked at in their report. They looked at alkaline electrolysis, that's on the top left-hand side. They looked at proton exchange, or PEM technology, and then anion exchange membrane and solid oxide. And then what I did, and you can see on the left-hand side, I said, well, what is the most mature technology? And alkaline technology is the most mature. It's adapted from what's used in the chlor-alkali industry, which has been with us for many, many decades. And then we go to proton exchange membrane, which is also a reasonably mature technology, but I've put there the comment not commercially proven at scale. And there we're talking about the multi-gigawatt scale. And then those bottom technologies are in the development phase. And sometimes, you know, you pick up in the media, for example, solid oxide. It looks very attractive, but it's really, you know, in the development stage. Maybe it'll become more prominent later, but it's definitely not commercially mature and not even necessarily ready for commercialization. Okay, and then on the right-hand side infographic, you can see that there are a number of trade-offs that we need to look at. There's the efficiency, the capex, and the opex, and the durability. And these gigawatt scale electrolyzers are still in the development phase. And then I make the comment at the bottom, from my own experience of working with process technologies, how they get commercialized and how they become commercially proven, and how new generations come in and the technology improves. This is a process that takes decades. So it takes decades to refine, optimize, and perfect these technologies, and some of them may be discarded. So this is an area of technology risk. Okay, so let's talk about what does green hydrogen cost, and can its cost be reduced? And this is from another IRENA report, very comprehensive and worth looking at. And there you can see they're showing a range of costs on the left-hand side there on their graph. What green hydrogen costs today. So, you know, anywhere from, if you look at the error bar there, from close to 3 to up to 6, but they're projecting, well, they've calculated a cost of close to $5 a kilogram as to what it costs to produce green hydrogen. Okay, and so and remember that this is at the factory gate. Okay, so this is the current green hydrogen cost at the factory gate, and I put there sort of plus or minus 5 kilograms. And then they've said, okay, but you know what could happen in the future, over the next few decades? You know, can we reduce the electrolyzer cost by 80%? You know, if green hydrogen takes off in a big way, we're going to start mass producing these electrolyzers, and as we start mass producing them, then we can produce them more efficiently and more cost effectively, and perhaps by 2050 we can reduce the cost by 80%. Ambitious, but certainly as an assumption it's worth thinking about. And of course, as you do ramp up production, you can reduce costs. Then can we get the electricity cost down from $53 a renewable electricity cost down as it's scaled out, you know, from 53 to 20 US dollars? That will help. Can we make them a bit more efficient? Can we operate them, you know, more hours? Can we deal with electricity storage and get them up from 3,000 to 4,200 hours, and so on and so on? You know, and if the planets all align, maybe in the future we can get to $1 a kilogram at the factory gate. Okay. So I'll just remind you that $5 a kilogram is equivalent to an oil price of about $250 a barrel. And the USA is proposing government subsidies of up to $3 a kilogram to kickstart green hydrogen industry and enable competition with grey hydrogen. And so, you know, as the government steps up and says, I'm prepared to subsidize this up to $3 a kilogram, well, then maybe a whole lot of projects that wouldn't ordinarily make sense may make sense, and that's why you're seeing a flurry of activity in North America. But those subsidies are going to cost a lot of money, okay? And it's certainly debatable as to whether those subsidies are justifiable. And if I were a US taxpayer, I would certainly be looking at this and thinking about that. Okay, green hydrogen capital costs. Here I'm going to refer you to a reference which I've got at the bottom, which is ISPT. The IRENA have also looked at capital costs, but I prefer this ISPT report because I think it's a lot more comprehensive, because they looked at total installed costs. Okay, in chemical engineering terms, they looked at both the IBL and very specifically at the OBL and all the offsites that you need, whereas IRENA focuses much more on the IBL, and they were a bit skimpy on looking at the OBL. Okay, and so this ISPT report is an excellent report to look at it in terms of what a green hydrogen project will cost, and they looked at a gigawatt scale plant, and so depending on which technology you looked at, they looked at alkaline and PEM technology, the two main competing options at the moment. And there you can see your gigawatt will give you, depending on which technology you use, about 165,000 tons or 150,000 tons of green hydrogen. The capital cost, the total installed cost, to a -25 plus 40% accuracy range with a proper cost estimate, is in the range of 1.4 to 1.8 billion euros, and there's a capital intensity figure, euros per kilogram and euros per kilogram per day of hydrogen. And let's see what those numbers mean, and that's what we talked about earlier in their 20 million ambition. Okay, so it implies, when you look at the projects, they tend to be between 1 and 5 gigawatts. So we're looking at 20 to 40 pioneering. And remember, I talked about the fact that the technology is still not fully commercially proven and it's being developed. So we're talking about pioneering mega projects, the capital greater than $1 billion of size 1 to 5 gigawatts. So the capital costs are in the range of 170 to 240 billion euros. Potential subsidies of up to $60 billion per year. Because remember, we talked about the fact that this $3 a kilogram subsidy is needed to get this industry going, because it can't compete because of the high hydrogen costs. So then I want to talk about the fact that the timescale to design, finance, approve, commission, and run energy mega projects. The first wave of projects constructed before 2030, they'll all be first generation pioneering mega projects. Let's assume that the EU is successful in their ambition to getting this 20 million tons built, and both within the EU and projects in other parts of the world, including potentially South Africa. Let's assume it all happens. These plants will need to reach FID very soon, because it'll take at least 4 or 5 years to build them and commission them. So there's no time for getting lessons learned and second generation technology and improvements and all of that. All of these projects are going to be pioneering first generation projects. The second generation projects, where the lessons learned and technology improvements are made, necessarily have to follow post 2030. There is no time for that pre 2030. Okay, and then a very good IRENA study, which I will reference here, on how do you transport hydrogen and what does it cost. And they looked at a number of options. They looked at pipelines, they looked at liquid hydrogen, they looked at repurposed pipelines where you convert natural gas pipelines to transport hydrogen, and then they looked at ammonia ships, where you convert the green hydrogen to ammonia, and then potentially even then you have to crack it back to hydrogen at the destination if you want to use it as green hydrogen. And the important point to look here, let's just unpack that graph. On the y-axis there, they've got the transport distance in thousands of kilometers, and then they've looked at the project size in millions of tons of hydrogen. And remember, we talked about a gigawatt giving you about 150,000. And there you can see, if you've got short distances that you want to move the hydrogen, pipelines are a potentially attractive option, and repurposed pipelines as well. You can certainly use that if you're moving it, over land and shortish distances. There was a flurry of interest in using liquid hydrogen, but according to the ARENA study, liquid hydrogen has a narrow range of attractiveness. Shipping hydrogen at -253 degrees is extremely challenging. I won't get into that, but there are a lot of references on that as well. But then if you're talking in the South African context, and if we were, for example, exporting green hydrogen from Southern Africa to Europe, for example, really what you're looking at is using ammonia. Okay, you'd need to convert the green hydrogen on site to ammonia and then ship it as ammonia. And ammonia is shipped today. There's quite a big global trade, and ammonia ships can certainly they're practical and commercially proven. And then just for completeness, and I don't think it's relevant today's discussion, on the left-hand side, there's a thing called a liquid organic hydrogen carrier. Not have time to go into that, but I don't think it's very relevant for our discussion. So, ARENA have also done a nice study into, but can we reduce the cost of moving hydrogen as well? So we say, of course, in addition to the levelized cost of production of hydrogen of plus or minus $5 a kilogram, you need to add currently today an additional plus or minus 3 kilograms to ship the hydrogen as ammonia. And I'm going to really just focus on the ammonia discussion here, because we've already kind of concluded that in the South African context, and in general, if you want to move green hydrogen over large distances, you really need to be looking at ammonia as the carrier. So when you add that $3 a kilogram, you come to the plus or minus $8 a kilogram I mentioned in the executive summary. And I just remind you that this is an equivalent to an oil price of $400 a barrel. Okay, so once again, dramatic reductions in costs are required for this to be feasible. Now, the one part of this ARENA report that I will express some surprise and skepticism about is to say, the ammonia production by the Haber-Bosch process is more than 100 years old. And it's highly optimized and very mature. I'd even argue it's probably one of the most mature technologies in the chemical industries. The history of the base chemical industry actually kind of started in 1905 when BASF built the first Haber-Bosch process in Ludwigshafen. And the scale and efficiency of those plants has literally gone over more than 100 years of innovation. So when people say that they're potentially they're big improvements in how we make ammonia, I express skepticism. Okay, so I say dramatic cost reductions in the production of ammonia are unlikely. And then just repeat the statement that subsidies are required to allow green hydrogen to compete. Nevertheless, you can see that ARENA is saying that maybe we can get high, the whole ammonia transport cost value chain down to even less than $1 a kilogram. I'll leave you to think about how likely that is. Then what I did, and I looked at a case study which I thought was very, very interesting to me. Will the hydrogen capital costs reduce dramatically? And I thought that LNG provides an interesting case study. So LNG business is about 50 years old. And I found this very, very interesting paper, which I've referenced there. looking at LNG costs over the last 50 years. So let me explain that graph to you. The green dotted line shows the capital cost evolution of LNG liquefaction plants over the decades. And so on the y-axis, we have, the capital cost measured in US dollars per ton of LNG. And you can see that when the business started in the early 70s, we saw a capital cost of about 900. And there you can see the capital cost evolution. Indeed, by the 90s or so, there were some reductions in the capital cost as this business grew. But then look at what happened after that. The capital costs rose significantly, and I just remind you that these costs are in constant dollars of 2018. So this is not a reflection of inflation. And interestingly enough, these the costs appear to be correlated to the oil price. The solid line there, the solid black line, is the oil price. And so when oil prices are high, LNG looks attractive, and then there's scarce resources and skill for projects. So you have a wave of projects. So it kind of bids up the cost, which is interesting to see. But I think the net conclusion that I'd like to draw from this slide is that if you look over the 50-year time period, we have not seen dramatic cost reductions in the capital costs for LNG. So I would just make the remark that perhaps it's not a given that there'll be dramatic cost reductions for green hydrogen production and transport forecast by IRENA. Will that actually happen in practice? Let me say it's uncertain. Then I want to talk about Liebrich's ladder. And I highly recommend following Michael Liebrich and the work that he's done. He's classified the various uses for green hydrogen. There are 32 applications on that slide. And then he's looked at the technical viability, he's looked at economics, he's looked at alternatives, and he has attempted in a collaborative way, lots of people contribute to this, at looking at what the best uses for green hydrogen are and which ones have alternatives and are potentially uncompetitive. Okay, and so if you look at that ladder, he starts and he's classified it from A to G, and he's also looked at what the alternative technologies are, and so you can see, those things in the sort of reddy color are technologies where there's no real alternative at the moment, and that's why they kind of end up at the top of the ladder. But he's also looked at technology and alternatives. So you can see there, fertilizer, ammonia, there's no real alternative, and that's why it's right at the top of the ladder. The same for hydrogenation, hydrocracking, and desulfurization are current applications. Methanol as well, and so you go down this ladder, and you get to applications where there are alternatives, and then you can see in the yellow, there's a lot of yellow in the bottom part of this ladder, where direct use of electricity and batteries is a potentially better alternative. So hydrogen is not necessarily competitive for all the applications it's being considered for. I'm not going to spend a lot of time on this slide because we're running out of time, but this is just a more detailed classification of Liebrich's ladder. It contains, all 32 applications. It's divided them up into the various end-use sectors, and buildings and heating, transport, industry and chemicals, and oil refining. And certainly you can just see here that buildings and heating and transport are, of course, and industry and chemicals are the major application sectors where we need to think about it. And there's lots of work that needs to be done in thinking about this. Okay, And I make the point here in that ticker box, the potential applications are complex, and each of the 32 applications merits its own investigation into the relative merits of green hydrogen in terms of competing options, carbon dioxide emissions reductions, cost and safety considerations, amongst many others. I want to just unpack an example based on calculations that I did, and together with Diane Hildebrand. So we just did a comparison of the use of green hydrogen for ammonia use as a fertilizer or its use for domestic heating. Okay, so let me explain the slide. Let's start with, on that infographic there, we start with 1 ton of green hydrogen. We're going to be producing it in the southern hemisphere. We're going to be shipping it as ammonia, and then we're going to be comparing it for use as fertilizer, or we're going to be looking at domestic heating in Europe. So we start with our 1 ton of green hydrogen. That gets turned into 5.7 tons of green ammonia, which we assume for the sake of this discussion is made in South Africa. And then we ship that to Europe. Now, if we use that green hydrogen as fertilizer, you can see on the left-hand side, we emit no CO2, and we're using the hydrogen for fertilizer. But let's compare it to the conventional route to making ammonia with methane. So you need 18.5 tons of methane for that. You'll have your conventional ammonia production, and that conventional ammonia production will release 51 tons of CO2 into the atmosphere. If we go on to the right-hand side, we take that green ammonia, we have to crack it back to hydrogen, so that's only 85% efficient. But of course, we emit no CO2. We compare it with the methane route, and there we only avoid 5.61 tons of CO2. So 1 ton of green hydrogen used for ammonia fertilizer avoids 51 tons of CO2 emissions. 1 ton of hydrogen used as domestic heating fuel avoids 5.61 tons of CO2 emissions. So from a decarbonisation perspective, it is much more efficient to use green hydrogen for fertilizer production. And here's a very nice infographic prepared by David Sabon from Cambridge University, saying, okay, so let's consider domestic heating in the UK using either green hydrogen or heat pumps. And there's a nice Sankey diagram. If you want to use green hydrogen, you're going to need 150 gigawatts of renewable electricity to drive that very inefficient process. And you can see from the Sankey diagram all the waste that's happening there and the waste heat that you're generating. Alternatively, you can just use green electricity directly using heat pumps. And green hydrogen needs 6 times more renewable energy provision than a heat pump. Multiple independent studies conclude that hydrogen is not preferred from a life cycle cost standpoint, and I reference those studies. Okay, did some calculations in terms of this efficiency metric of carbon dioxide reduction potential for selected green hydrogen applications. I took you through the 2 examples that I did there. Green ammonia used for use as a fertilizer, through to fuel cell electric vehicle, fuel cell electric truck, hydrogen as a heating fuel, and e-kerosene for aviation. Okay, so what is the objective of implementing green hydrogen? If it is to decarbonize in the most efficient manner, then different applications for green hydrogen show a wide range of carbon dioxide reduction potentials. Currently, a scattershot approach to green hydrogen applications is being pursued, even where more efficient, cost-effective alternatives exist, as if green hydrogen is abundant and cheap, which it is not. Okay, I'm going to look for some guidance on from the course organizers, because as you can see, I've got lots of material. I can skip to the conclusions, or I can spend 1 or 2 minutes, or maybe another five minutes, or whether you would like to pause now to allow the panel discussion to start.
No, please continue, Bruce. Please continue. Okay. We've got time. Thank you.
Okay. I reference a very good paper, okay, by someone from the Max Planck Institute. And I've been actually corresponding with this man, Max Vanna. He started looking at saying, so, okay, the EU is going to import 20 million tons of green hydrogen by 2030. What are we going to use this green hydrogen for? And what infrastructure do we need to build to be able to use this green hydrogen? Because there's lots of talk about making it, but there's actually not that much talk about, well, what is it all going to be used for? So he looked at two examples, okay? And so he looked at it as a hydrogen, for generating electricity, as an electricity storage option, which is one of the options that's been looked at. So he said, well, what would a 1 gigawatt power storage for 24 hours look like, okay? To deal with, you know, lull and intermittent in electricity supply. So here he says this is going to either require a large cryogenic storage vessel of 22,000 cubic meters, or storage of 145,000 cubic meters in a salt cavern at 150 bar. So first of all, he kind of says, how technically feasible is this? But let's not even go there. Let's say it is technically feasible. Irrespective of whether it's technically feasible, if a market for 20 million tons per annum of hydrogen is to be created by 2030, decisions will, and I would say not soon, like this year, will need to be made regarding what applications the hydrogen will be used for, and the projects initiated to construct the infrastructure so that it's ready in time. You know, building this sort of infrastructure from FID to commissioning is 4 years. So just think about that schematic process chain indicating that Max Vanna has put out there as to what is required in terms infrastructurally to be built in the European Union. Then he looked at another example. He said, okay, but let's assume that we're going to convert service stations for fuel cell electric trucks. Okay, they're going to be plying the highways in Germany, and green hydrogen is going to be used to do that. Okay, so he said, well, right, okay, if the hydrogen, and he looked at 10,000 tons per annum service station, which he calculated would be a big service station. So if the hydrogen is sold as a liquefaction plant consuming 13 megawatts of electricity will be required, together with a cryogenic storage vessel of about 210 cubic meters. Alternatively, two-stage compression to 700 bar is considered, consuming 2.5 megawatts of electricity and just over 2,000 cubic meters of high-pressure storage vessels. And then he says, and quite correctly, that the operation of the hydrogen filling station will resemble the operation of a chemical plant rather than a conventional service station. So all the stuff that you'll need for a chemical plant, you'll need, you know, a production manager, you'll need all the infrastructure that a chemical plant. This will be a lot more complicated than a conventional service station selling diesel. And then to reach net zero, Germany will require 140 such service stations, each consuming about 10,000 tons per annum of hydrogen. Now, the question of whether sufficient demand from fuel cell electric trucks will be available by 2030 to match the supply and the infrastructure built is still an open one. As we speak today, you cannot buy a fuel cell electric truck. There are only prototypes out there. So, and then the open question is, if the trucks are available, let's assume that they are available, it is still not clear whether freight companies will choose fuel cell trucks or battery electric trucks. This debate is still raging, and it's not known whether the battery electric trucks will win or fuel cell electric trucks. So the question of whether sufficient demand from fuel cell electric trucks will be available by 2030 to match the supply and the infrastructure built is still an open one. So, given the high cost of producing and transporting green hydrogen, alternative technologies also need to be considered. Some applications, like nitrogenous fertilizer production, have no known real alternative, but it will be expensive and the implications for food costs will be significant. Direct use of electricity for many applications is cheaper and more efficient. And then I pick on the domestic heating is cheaper and more efficient using heat pumps. But there are issues there, of course. It will requires a replacement of existing boilers, which is costly. So, I mean, if you go into Europe and people have, they've just installed a brand new natural gas boiler at the cost of, let's say in the UK, of several £1,000s. And now you say, no, well, why don't you just rip that out and put in a heat pump system, which will also cost you several £1,000s. You can see that people might get a bit grumpy about that. And so that's something to think about. And obviously, but certainly from an economic and thermodynamic and decarbonisation perspective, heat pumps are a clear winner. I'll make the comment that aviation is likely to become significantly more expensive because yes, you can make aviation fuel using green hydrogen, but it's extremely inefficient, and that efficiency turns into high costs. And use of green hydrogen as a chemical feedstock implies significant increases in the cost of chemicals. And an important issue here is a key unresolved problem is how to remove renewable energy to densely populated countries like Japan and parts of Europe. So that's driving the whole green hydrogen discussion. I would just mention here, and it's something that I've looked into quite a lot, not today for the discussion today, but there are even alternatives to that, which is high voltage direct current cables, and indeed even submarine cables. And so that's certainly something that's being looked at. But a problem for the world is how do we move renewable energy to densely populated countries from countries which have abundant renewable energy potential. Then I want to talk about, and I have this T-shirt, Pioneering Mega Project Risks and the Iron Law of Mega Projects. It's one of my favorite laws. I was burnt by this law through my career many times, okay? And I reference the Oxford academic, Ben Fleifberg, who's written books about this. And let me summarize some of his findings here. So mega projects are classified as projects that cost more than $1 billion. He's done immense research on this. And his iron law of mega project states, over budget, over time, under benefits, over and over again. 9 out of 10 mega projects have significant cost and schedule overruns. And why does this happen? And the research has shown that mega projects are driven by the 4 sublimes. And here we're talking to a bunch of engineers. And engineers are very guilty of the technological sublime. It describes that excitement. In fact, he doesn't use the word excitement, he uses the word rapture. Describes the rapture engineers and technologists get in pushing the envelope. That's what we're trained to do. What could be more fantastic than working on a pioneering project and being at the cutting edge of making things happen? I've done it, it's been interesting. I enjoyed it. It doesn't necessarily make money. The political sublime describes the tendency politicians have for constructing monumental infrastructure. Politicians love pioneering mega projects. And the economic sublime, it describes the delight business people and trade unions making lots of money, and the service providers, of course, will tell you what a fantastic project you've got. The aesthetic sublime, that's not necessarily as relevant in the process industries. And then there are additional risk factors. There's pioneering technology, remote locations, west coast of Southern Africa, lack of skills to execute a mega project. And then if you think size and reputation helps, no, it doesn't. Chevron's Gorgon LNG project in remote Western Australia, the original budget was $34 billion. By 2014, costs had risen to $54 billion. It nearly bankrupted Chevron. Pioneering gigawatt-scale green hydrogen projects in Southern Africa are virtually guaranteed to have significant cost and schedule overruns. I'll take a bet with anybody, and take your money off you. Once once an FID number is published, that the project will not meet the cost and schedule promises in the FID document. And then just a last slide, just to mention, and I think we can end here. I don't want to talk too much about safety, but there are some safety issues. You can look at these slides afterwards. I don't want to spend much time talking on that, just to say that safety is an important consideration for hydrogen, and hydrogen is dangerous, and it's more dangerous than natural gas. I'm not going to talk about this slide, that you can look at your leisure. And then just a slide. Let me not even talk about this. Look at it at your own. The Sasolburg project is a potential project. It's in an extremely remote location, and I would definitely say that the iron law of mega projects will apply to this. And then there's a 100 billion Kucha green ammonia project study announced by Hive Energy. At least that's in an area where infrastructure exists, and they can build off infrastructure, and they're looking at making green ammonia. Let me end off my presentation there so that we can go into the panel discussion.
Thank you, Dr. Young. First class. Thank you for that. Let me take back the presentation panel. Thank you, colleagues. I'm going to share with you my screen. Professor Lockhart, I'm going to bring you on board now and take us straight to the panel session. If you may come on and lead it for us. Over to you, Professor Lockhart. David.
Thank you so much, Pat. Just want to also thank Dr. Bruce for a wonderful presentation, very illuminating, and really bringing reality to a very important topic. I think most of us, have heard the buzzwords and really have taken this in at a very superficial level, but this really sort of grounds us in some of the data and the realities of bringing hydrogen into this energy space. Pat, I just want to ask though, are there any specific questions that have come through from the attendees that we need to run through, or can I open it up to the panel to ask some questions to Dr. Young as well?
Yes, please feel free. Thank you. Thank you. Okay, if the panelists could put on the cameras and come and join us. I've got 2 questions on the chat box, and I'll share that with you as you get ready.
All right, great. Colleagues, if you can just come back online. Thank you. Thanks. I've prepared a couple of questions. So, Pat, as you're bringing in the questions from the rest of the attendees, maybe we can run through these very quickly. So maybe we can start, and I'll direct these questions to Dr. Young, and then the other panelists can come in with some comments as well. But the first one that I had was well, in the context of the current energy crisis in South Africa. So, what are the realistic opportunities for uptake of hydrogen, particularly at a domestic level? So not so much at an industrial level, but at a domestic level. Is it possible, or do you see any realities for uptake of hydrogen at a domestic level, at least within the medium to short term?
So do you mean, for example, putting hydrogen into Egoli gas in Johannesburg?
Yeah, possibly, or even have these kind of decentralized hydrogen generation facilities for communities or even homes.
So I would like to think that the example that I provided there, the work that David Sabon and Cambridge has done, has kind of suggested pretty much that that domestic use of green hydrogen is simply not a good idea.
Mm-hmm.
So, I would nail my colors to the mast saying, I don't think that's a very good idea.
Okay. Is this specifically an economic issue, or is it a combination of factors?
It's a combination of factors, but I would start with it's an enormous waste of renewable electricity.
Mm-hmm.
Okay. We should rather just supply the renewable electricity directly.
Thanks. Yes. Thanks, Dr. Young. And then as a follow-up question to that, so I read in an ICME report from, I think it was March of this year, where they looked specifically at the categories of costs associated with the generation of hydrogen. And as these capacities increase, it's actually the cost of the renewable energy that is contributing a majority share to that overall cost. And do you believe that, we've got a current level of supply probably at the megawatt level? So you were mentioning, gigawatt projects in your presentation. Do you feel that we can even get to a gigawatt level here in the global south?
So I don't think if in the global south we're building gigawatt scale projects, I don't think the local market, certainly for a long time, would support that. We would be looking at export projects. And so let's go, if you go down that route, you would be looking at, I don't know, for example, signing a contract with the EU or with the German government, that you would be exporting ammonia, and they would need to sign, I think, a take or pay contract, 20-year take or pay contract at prices which would be satisfactory for that. If that could happen, then of course we could look at trying to develop a local market to some extent off the back of that. But I think the anchor tenant would need to be a major export contract with sovereign guarantees, okay, from something like the German government.
What would then be the draw card? What would be the favorable thing that brings these more established economies to our backyard to partner with us to actually take these hydrogen projects forward? What can we offer them?
I think that's a very good question, and I would certainly say that obviously what we offer them is renewable energy potential. The driver for all of these things is wind and solar availability, and desert areas or areas where land is abundant, okay, and so regulatory approvals and local communities and things like that are not a major concern. But of course, we'll be competing with places like Morocco and North Africa, which will offer some of the same things. Having said that, by the time you're moving ammonia, I think that whether you move the ammonia 2,000 kilometers by sea or 10,000 kilometers by sea doesn't make that much difference. So South Africa can in principle compete with Morocco. But I do think that if you choose remote locations like Buchubai with no port infrastructure and no local infrastructure, I must admit I struggle a bit. But if you look at Kucha, maybe that's not so bad. There's quite a lot of infrastructure there, and there's government support. So that's potentially something we can look at. And I certainly think, in principle, we can compete with places like Morocco and Egypt.
Okay, thank you, Dr. Young. Maybe just to bring the rest of the panelists in, if I can pose another question. So you did mention in your presentation that sort of like distribution networks for hydrogen are going to be sort of a critical factor for sort of determining its uptake. What are the specific areas of development that maybe electrical and chemical engineers in South Africa would be able to contribute to, insofar as the hydrogen project is concerned?
Yeah, that's a good question, and I'm not sure I'm well placed to answer that one. So you know, I do think that there's this wave of interest in hydrogen, and if you position yourself as a service provider, I think that there's a lot of work in green hydrogen that's coming. I think you need to be very cautious if you're a project owner. But if you're a service provider, you know, you follow the money. And while there's work here, I think you should follow that. So certainly from a chemical engineering point of view, this is chemical engineering, and there's no reason why chemical engineers shouldn't follow the trend and make a career out of it. I would just caution, though, you know, and the chemical industry is very prone to booms and busts. Okay, and so you know, if you put all your eggs into that basket, okay, be conscious that, you know, a bust could come, and then I would certainly, as a young chemical engineer, put my eggs into more than one basket.
Okay. If I could just maybe ask both Dave and Maggie, and with their experience on the hydrogen interest group, to maybe comment on this as well. I mean, you have been speaking with some of the professionals in the space. So have you maybe come across something with regards to the contributions that chemical engineers specifically are making in this space?
Maggie, do you want to go?
You go, Dave.
Look, I think you know, there's a lot of research potential and a lot of research going on. You know, I mean, Bruce has pointed out that the arena is saying that to bring the cost of green hydrogen anywhere near a commercial level, there needs to be an 80% reduction in the capital cost. I mean, that's huge. That's massive. You know, and when you think about the way that these electrolyzers are put together, they're effectively, you know, packs of cells. Now, what is it that you're going to do from a research point of view to actually reduce the cost of a cell by 80%? So in that regard, I think there's massive potential for research, and that's been borne out by the amount of money which government is putting in through the HySA program, where they subsidize, or not subsidizing, they're providing funding for research at a number of different universities around the country. But if you say, well, what potential is there for a new graduate or new engineers Bruce has referred to? Right now, I don't think there are opportunities unless you go into an organization that's already producing hydrogen. So either a refinery and or Secunda, because the experience of working with hydrogen is obviously going to be a critical feature in the future. You know, the explosive limits for hydrogen are wide, so the potential safety risk is massive, I think. Every time I raise this in other quarters, people kind of poo-poo the thing, but I personally think safety is a big issue that we mustn't overlook. So yeah, at this stage, I don't think there's a lot available. Once we start getting projects on the ground, it'll be a different story. But Maggie, you might have a different view.
No, Dave, I do concur. And I think Bruce has been bringing up the cost of these mega projects. So I think in the South African economic climate, I think that is a huge challenge. And also, if you're looking at the graduates that we are producing, So in order, they need to go into a mature industry, companies like SAIChE and so on, for them to be really making a big difference. Yes, Dave, there is research going on, but for our graduates, they need to be, for them to get that training, they have to be in major companies. But on the other end, of course, we still have to be planning for the future. So that funding coming from government and being poured into the research institutes at postgrad level is also important, because if we don't do that, then as you say, if you're looking at the size of those electrolyzers and so on, you know, it has to be a multi-pronged approach. I mean, as from an academic point of view, we also got to be, the curriculum has to include things like renewable energy and get graduates thinking about hydrogen and not thinking that, you know, I'm going to work for a major industry, but maybe sometime down the line, look at maybe becoming entrepreneurs, engineers banding together, be it electrical, chemical, mechanical, to help with these major projects. So I just want to emphasize again what came across from Bruce. Yes, it's going to take a lot of money, both private sector and government, to bring about these mega projects. And of course, location is very important, Bruce. And in this country, we have other challenges like water, housing, and education, and so on. So that brings in another factor. But I think as engineers, I think we just need to teach the graduates, or if we are training engineers, that, you know, we have to look at alternative ways of producing energy. And of course, it's always about the cost. Thanks.
Thanks, Maggie. If I can bring Pascal into the conversation then, from the electrical engineers side. Pascal?
Yes, perhaps I can also contribute. So the other head that I wear, I'm actually the chairperson of the manufacturing working group under the Federation of African Engineering Organizations. So I am privy to several reports and studies that highlight the viability and potential benefits of green hydrogen in Africa. In fact, I think in one of the reports, they estimated that Africa could produce around 5,000 megatons of hydrogen per year, which is equivalent to the global energy total supply for the year for the world, basically. They talk about harnessing solar power to create green hydrogen in key African hubs such as Mauritania, Morocco, Southern Africa, Egypt, the likes of those, where they say they can accelerate low carbon economic growth across the continent, basically, and reduce the emissions by, I think the report said 40%. So the industrialization potential of green hydrogen in Africa is also sort of recognized in that report. That report actually suggested that green hydrogen could sustainably industrialize Africa and boost the GDP by around, they were estimating 6 to 12% in those countries that I mentioned. Because they're saying what Africa's abundance of renewable energy resources, including your solar and your wind, the region is well positioned to capitalize on the production and utilization of green hydrogen. And furthermore, certain projects and initiatives that focus on green hydrogen production, some of the countries actually have been announcing such projects that they are looking into. Namibia, for one, they have announced something like $9.4 billion US dollars green hydrogen project, which they scheduled to enter production by 2026, aiming to generate 2 gigawatts of renewable electricity from that. But however, yes, to fully leverage the potential of green hydrogen economy, I think the African manufacturing sector needs to embrace and to adapt the evolving energy landscape. And that may involve investments in renewable energy infrastructure, obviously, and in the development of hydrogen production and storage facilities, the integration of green hydrogen technologies into the manufacturing processes, etc., etc. So collaboration between the government and the private sector entities and international partners will definitely be crucial in building the necessary capabilities and supporting the growth of the green hydrogen economy in Africa if we were to venture into that realm fully.
Okay, thank you, Pascal. Line was not very clear, but I think most of us managed to hear the comment there. Bruce, just a quick one then. The final question that I had was particularly on hydrogen in steel production. And the question is, not from an energy point of view, but actually as a reducing agent in the steel process. Specifically talking about decarbonization here, because I know that there's a lot of coking coal that's used in that particular process. But is there any comment that you may have regarding that? So using the hydrogen as a reactive material in that process?
Yeah, so if you go and look at Liebrich's ladder, you'll see that that's quite close to the top of the ladder. So replacing coking coal is a very interesting application of green hydrogen, and I think there's merit in it. And in terms of the prioritization, as it currently stands, if you go that route, the cost of the green hydrogen is what I call a fairly small problem, because when you look at the cost drivers for steel, it can somewhat afford the price of hydrogen. As I recall from the studies that I've looked at, it increases the price of the steel. I think the numbers I have in my head, and only stand to be corrected, are in the order of 10 to 15%. And there are, for example, BMW has already said, well, it's prepared to actually absorb that cost, and as part of its marketing, then say, but we use green steel, and I do think that the concept of using hydrogen for iron, for direct reduction of iron, has got legs. It does also, and I'm not a steel expert, does need to compete with using electricity directly. But I do think that the whole concept of direct reduction of iron is one of the better applications for green hydrogen.
Thanks, Bruce. Lizelle, is there any comment from your side? I know that you work more on the metallurgy side.
Yeah, I've seen there are actually a few plants already where they're doing direct reduction with hydrogen. But these are like in countries like China and so on, and that then poses the challenge again. If we're going to export green hydrogen, how are we going to transport it? They specifically have changed their steel production plants because of the emissions that they cannot handle, and so they some of these plants actually have like a combination of hydrogen and the carbon in them. So I think perhaps in that sense, for the South African economy, if we can make localized steel that we can export, that would probably be economic driver for us as a country.
Okay, thank you. I see a hand up from Dave. Dave, go ahead.
Yeah, thanks, David. Just to pick up on Lizelle's point, I mean, I read somewhere that ArcelorMittal is looking at doing something with hydrogen at their Saldanha plant. Does anyone on the panel actually know any more about it? Is it serious, or how's that project going? Is it still an idea, or is it actually going to do anything? Do you know anything? Maybe Bruce or anyone else?
So I know enough to be a bit dangerous on this, but I'll venture my opinion. Yes, I'm aware that that's being looked at, and I think that SAIChE is looking at that. I've heard from from my former colleagues and corridor chat that that's something that's potentially there. And I will put nail my coast to mast. I think that's a better thing for Sasol to look at than Buchuba. Okay.
Okay. Colleagues, just now coming up on quarter of an hour to go. Let me then take it to a more controversial question. So do you think that going into the near future, we're going to see more pressure perhaps from government or the political arena to get companies to get on board with the hydrogen project, as I'm calling it? Yes, there.
If you look at where these projects are being promoted by government, it is primarily through the form of subsidies. And as Bruce has pointed out, you know, it's a substantial subsidy. I mean, $3 a kilogram is quite a big number. And if you consider where we are as a country in terms of our current economic status, I don't think the government's got that kind of money to do it. So I don't see any form of government incentive over and above what they're doing through the science and technology route right now. So I think unless as part of the take or pay agreement that Bruce referred to, that we might be getting into via one of the more developed countries, if that pricing structure doesn't pick up that $3 a kilogram number, I think we're going to battle to get green hydrogen projects going in a serious way in the country. But maybe I'm being pessimistic.
But could there be some point reached where there's no longer an element of persuasion, but then compliance insofar as the use of green hydrogen is concerned? Is that perhaps on the horizon, Bruce?
Just look at it differently. $3 a kilogram is now 60 rand a kilogram of hydrogen. I don't know how that would compare with the cost of CO2 on emissions. So, you know, that to me is where the driving force of anything is going to come from. If it's going to cost you more to pay for CO2 emissions than it is to pay for producing hydrogen, then you're going to produce hydrogen. But it's going to be, that's going to be the driver, I would think. But perhaps I'm seeing it wrong. Bruce might have a different view, or anyone else.
I think I agree with everything you say. So, but I would make the remark, and now I would kind of go up a level and say, let's look at this from a global perspective. And I'm not saying the world is good at doing that, okay? If we want to decarbonize, then, and I'll just pick nitrogenous fertilizer, ammonia. Well then, guys, one of the most effective things we can do is use green hydrogen for fertilizer. But then we have to come to the thing of, okay, but who's going to pay for it? Because, and what Dave said is the South African government can't pay for it. I agree, that's correct. But if the EU and the world, as we get to COP28 and COP29, we're going to have to start facing these questions as global citizens as to how do we decarbonize. Now, in the messy political environment that we live in, I don't think those conversations are even happening yet. But if you look at it purely as a technocrat, okay, which I'd like to think I would say, well, guys, we need to start having the conversation about how does the world transition to green fertilizer, because it's the right thing to do, and who's going to pay for it? That would be my sort of high level.
Okay, so in other words, choose the battle. Thanks, Bruce. I was just about to say, so choose our battles wisely.
Yes, no, absolutely.
Yeah, okay. Okay, that actually is the wrap from me in terms of questions, but I'm not too sure whether there's anything that's come through on the Q&A.
Yes, yes, there has been Prof. David. If I may go through the questions. Thank
Please.
you. One from Stefan Duplessis. On the comment of $400 per barrel, Bruce, she wanted to find out if the energy produced per unit weight, given that H2 has 3 times the energy density to that of oil, how would that comparison reflect on the cost as of $400 per barrel? Just trying to draw the linkage between energy density.
So, and I'm happy to go into the details of the calculation and to even supply the calculation. I've double-checked the calculations and got others to check the calculation. So it's a very simple, it's a very simple calculation. Actually, a couple of assumptions about densities and things needed to be made, and refining margins and things like that. But I don't know whether we want to go into the details of their calculations. I would say I'm convinced they're right, and I'm happy to supply the details.
Right. No, thank you for that. And again, Janet Gillespie has also posted a similar question. How does that compare with coal, the energy density of coal?
So I haven't done the coal calculation, and it depends on what the coal price is. But I mean, coal is pretty energy dense. Okay, so but coal will be much cheaper than hydrogen.
Much cheaper, yeah.
Yes.
No, thank you for that. There's one from Hugo. He wants to check on the leakage rates in hydrogen gas if it's transported through repurposed natural gas pipelines. Any comment on that?
Now, that's not my area of expertise, first of all, what I will say. And then secondly, I will say that hydrogen is a very leaky gas. Okay, anybody who works with hydrogen knows that it's more leaky than methane. So, it's a tiny molecule. It likes to leak. Anybody who's worked with it in the lab or industrially knows that. Okay, but containing hydrogen is tough.
A big challenge.
Okay.
Right.
Yeah.
Janet Gillespie makes a comment around hydrogen and water. Given South Africa's be a water scarce country, how much water would we use up in this process? Can we use seawater?
Yeah, I get this question a lot, and I understand the rationale behind this question. But actually, when you look at green hydrogen production, okay, the use of water, even if you were, let's say, on the west coast of South Africa in the desert area, water is not a driving factor for green hydrogen production. Yes, you need high purity water and you need some water, but I mean, if you compare it's not a cost driver. So you can even afford to desalinate water and purify it, okay, which is not a cheap thing to do. And if you look at the amount of water that a coal power station uses compared to the amount of water that you're going to need for green hydrogen production, it's a logical question, but when you delve into the numbers, you kind of step back and say, water is not the biggest issue here.
Michelle Rivola has a point on, or a comment. She says, you cannot just feed hydrogen into an LNG or LPG gas line. The materials are a limiting factor. You will need to blend hydrogen into the gas line up to an approximately 20% to increase the calorific value. So there's a comment from Michelle. Don't have to respond. Let's go to Verusha.
I agree with her.
Thank you. Verusha Fester has a question. What should we focus on in terms of research to make a significant contribution to the success of green edge in South Africa? What would be your priority research that we need to focus in?
Who wants to go first?
Academic colleagues?
I want to come in and I want to say that from a chemical engineering point of view, I think we need to work on the loss prevention, risk assessment issues, and to a certain extent we can also look at systems approaches and the atom efficiency of these different configurations that are used for the generation process. But my feeling is that, you know, the technology is moving at the rate at which it can move. I don't know whether Bruce would agree with that.
What technology specifically are you referring to?
I'm just talking about the generation technology. So you spoke about, in that little image on the slide, the four main types of generating units.
Electrolyzers.
Yeah, the electrolyzers. So I think that is actually moving at the rate at which it can move. I think those other aspects are the ones that really need to be looked at if hydrogen is going to be taken up at a commercial level.
No, thank you. McDonald Subela has a point. Dr. Bruce, you spoke about a short pipeline with a short distance. How short is short distance?
So if we go back to that, if we go back to that slide, I think it's there, you know, up to a couple of 1,000 kilometers. I mean, I'd have to pull up that slide again.
Okay.
But you know, pipelines typically, let's just talk about natural gas pipelines, because they're the archetype, I think. You know, go from tens of kilometers, and long ones are up to thousands of kilometers. 2,000. I think if it starts once going over 2,000, then becomes problematic. But you need, if you're having those sort of long pipelines, the longer the pipeline, the more volume you need. Okay. So, you know, in Europe, when you look at these long pipelines, there's an enormous amount of gas going through them. So building pipelines is always a chicken and egg problem. You need the demand to justify the pipeline.
Right. No, thank you for that. Frans van Neerjin has a point. If you start with renewable energy, then through the electrolyzer and then through a fuel cell, you will get electricity again. That efficiency is very low with little advantages. Your comments, please, Dr. Bruce?
I agree. So that's the comment. And there is a slide, but which I didn't talk about a lot. That it's problematic to use hydrogen as an electricity storage technology because it's very inefficient.
Right. No, thank you. Daniel Francis has a question. Is there a potential green hydrogen market for use in South African steel industry for producing and exporting green steel? No, thank you. And Professor Lizal did answer that. Thank you. I'll pass that one over. And Lutando Mkizi has a note. What research opportunities do you foresee for students in the field of chemical engineering, specifically in terms of advancing green hydrogen production, storage, and utilization technologies? Prof. David, any thoughts there? I think chemical engineering students, they want to.
You know, I specifically said that, you know, we've already got these programs that exist within our frameworks for development of the electrolyzer technologies, but those are obviously moving at the pace at which they can. I think the one thing that we highlighted is that, you know, connected to this is going to be a whole of other issues that chemical engineers can contribute to, being, you know, on the risk assessment side, on the you know, the atom efficiency side and so forth. So maybe those are kinds of the things that our students actually should be taking a closer look at.
Right. No, thank you for that. I've got a question here from Atanda Raji. How is green hydrogen export drive contribute to renewable energy beneficiation in South Africa? I think we've answered that a few times. Any additional comments for Atanda?
The only thing I would say is that we have to get the export drive before we can even think of local beneficiation because of the volume requirements.
Right. And again, someone's got to give that subsidy. There's a comment here from Louis Zanberg. Good day, Dr. Burce Young. very interesting presentation, and in your space of DRI production with hydrogen. Can you elaborate a little bit on the viable solution again for the iron and steel industry going forward? I think we've answered that also. All right, Louis, I think we've covered that. And Titus Mate, Dr. Titus Mate from SAIEE, what policies could be considered by government to accelerate the introduction of green etch in the South African market? I think we've covered that also. Need lots of money, Dr. Titus. Let me go to Linda Jewell. Question for Dr. Young. You've ruled out LOHC. Can you please explain why you think this is not a feasible option? Linda? Dr. Burce Young, your LOHC on the side of the graph you had.
Yeah. Yes, I don't think I necessarily ruled it out. I think that's a bit harsh. I don't think it was particularly relevant for today's discussion, and it didn't apply to sending large quantities in the South African gigawatt context. Okay, so Linda, I don't think I'm ruling it out. I'll also confess that it's on that basis I didn't study it, and you probably know more about it than me. Okay. So I will also bow to your superior wisdom on that. But I'm just saying that if we've got a 5 gigawatt project in South Africa and we want to export it to Germany for argument's sake, I don't think we're going to be using LOHC.
Right. I'm going to jump through some of the questions here because we've answered them. But there's a point here from Atanda Raji. Carbon taxation is an instrument that can change the game altogether. Carbon taxation is an instrument. Any comments on carbon taxation, Dr. Bruce?
So carbon taxation is absolutely central to this whole discussion as to how the world is going to decarbonize and how carbon taxation plays out, and things like the EU carbon border adjustment mechanism, which I've only in the last year become aware of and studied, and a part of decarbonization. It's central to the whole debate about decarbonization. So completely agree with that. But it's an evolving field, carbon taxation, and most of the world still doesn't pay carbon tax, and it's very political. But to the extent that we're going to be successful as a global population in dealing with decarbonization, carbon taxation is absolutely central to that discussion.
Right, I've got a comment here from David van Vuren. In the presentation, mention was made about a bit of hydrogen being generated when doing CO2 capture and storage. Any further explanation on that, Dr. Bruce?
Can you repeat that question, because I'm struggling to understand it?
Sorry. In the presentation, mention was made about a bit of hydrogen being generated when doing CO2 capture and storage. I want a little more clarity on that.
I'm not aware that I said that. Okay.
Yeah, I'm not so. Yeah, I didn't pick that up. All right, David, we'll ponder on that one.
Sorry, sorry, Pat. I think that what Darby's trying to ask is, what is the viability of carbon capture in order to produce blue hydrogen? That would be my interpretation of the question.
Okay, that's the question.
And yeah, if that is the question, then I would say we've got no chance in South Africa of producing blue hydrogen. But Bruce might have a different view.
No, so I absolutely agree with you completely, Dave. I mean, as far as I'm aware, and I'm not an expert on carbon capture and storage, but we don't have the geology for it. So that's a huge problem. And I will also tell you, which is the subject of a whole nother discussion, that I'm a carbon capture and storage skeptic as well. Okay, and I'll be more skeptical than on green hydrogen. The promises and forecasts made on carbon capture and storage, if you go and delve into the history of that, lots of promises and lots of over-promising and under-delivering has been going on there.
Right. We're 12:59. Let me take a last one from Professor Kapil Murthy. Kapil makes a comment that Tesla CEO Elon Musk calls hydrogen the most dumb thing I could possibly imagine for energy storage. So given today's discussion, this seems to be something he's right about again. So that's a comment from Professor Kapil Murthy referencing Elon Musk. Final comment, Dr. Bruce?
Yeah, well, of course, I think he's taking an extreme position, which I wouldn't agree with entirely, but there's some merit in what he says, and of course he would say that, wouldn't he?
Right, he's a businessman.
No, he said so but there is some
vested interest.
Yeah.
There's no vested interest in it.
Exactly.
Now, thank you, colleagues. I think we've reached our time. We 1300 on schedule. May I extend a special appreciation to our presenter, Dr. Burce Young, and to the rest of the panel. First-class work. Thank you, colleagues. Thank you for the leadership. And thank you to both the institutes, South African Institute of Electrical Engineers and South African Institute of Chemical Engineers, for hosting this webinar. The webinar and the presentation would be posted on the SAIE YouTube channel, and it will be available for you to go through in detail and to continue the conversation with the respective institutes as we go into time. Thank you very much. Enjoy the rest of the afternoon, and let us say goodbye from Johannesburg. Thank you. Bye-bye.
Is everyone?
Thank you. I'm ending the webinar.